Hey guys, have your notes here for section 8.3 day 2. And just to kind of clarify, yesterday, in yesterday's video, I demonstrated with a paper plate, and we found the area of a paper plate over and over and over again. And I'm going to do something similar to that today. However, your book and many other calculus videos out there don't call it the paper plate method. They call it the disc method. So like a disc, like a solid disc, almost like a Frisbee, but completely flat. That would be the disc method. And then today's notes, same concept, yet a little different. This is called the washer method, not as in washing machine, but as in washer, the flat metal piece that goes behind a bolt that you might be screwing in for additional pressure. The washer method. Okay, so here's what we're doing. We are going to be looking at some area on a two-dimensional coordinate plane. And this time, the area doesn't extend all the way to the axis that we're going to revolve it around. For example, yesterday, we might have looked at the area under this top curve, and our area went all the way down, touched the x-axis, and we sent it around the x-axis. So what we got yesterday was a completely solid three-dimensional object. It was completely full of something like concrete, or I don't know, something. It was completely solid. Well, today you're going to see that our area that we're looking at, we're going to take this shape and we're going to revolve it around an axis, but it doesn't touch the axis. I mean, maybe just right here at the tip, but there's going to be some empty space in here after we revolve it around. Okay? So we're going to take this like width here, and we're going to send this little sliver all the way around the x-axis. It's going to create a circular shape, but it's going to be hollow on the inside. And here's a couple of pictures of what it looks like taking it around the y-axis. So if we just take one of these around the y-axis, you can kind of see that it's going to create a circular shape, but it's going to be hollow in the middle. And then the resulting figure would be almost like a bowl, I guess, that you could store stuff in. All right, so the cool thing about today's notes is we're looking at the same two functions over and over and over again. So I've drawn them, and then I kind of got to cheat, and I used copy and paste to just copy and paste them into the other problems that we're getting ready to do. So go ahead and get your drawing set up. You should be able to do this completely on your own. Graph each function, shade between them, and then we'll figure out what to do with them. Okay, so the first one says, let's take this shape. I'm going to call it a banana. I hope I can call it a banana. It looks kind of like a banana. We're going to take the banana, and we're going to send the banana around the x-axis. And you can see that what would happen is it would be kind of like a bowl, but the outside of my bowl would be completely linear. The inside of my bowl would have a very odd shape, but yet it could hold stuff. It would have empty space in the middle. So we're going to approach this the same way we did yesterday, only with an extra step. So what we're going to do is we're going to take the outer function, revolve this around. I think you can see that my blue function would be what would be on the outside. We're going to take the outer function, we're going to revolve it around just like we did it yesterday. We're going to pretend for just about a minute that it's completely solid. There is no place to store anything. There is no bowl. It's just completely filled. And we do that by taking the blue function and sending it around the x-axis. And then we take the red function and send it around the x-axis. Now keep in mind, when I send around the red function around the x-axis, I'm sending all of this around the x-axis. And what we're going to do is we're going to find the volume of the red, and we're going to like scoop it out to create a bowl. So we're going to do two separate problems. We're going to send the blue one around, pretend it's full, it's solid. Then we're going to send the red one around. We're going to scoop that volume out. Two separate problems, like two separate integrals. So here we go. Let's look at the outer first. And if I kind of mirror it on the other side, see what I'm doing? Same way as yesterday. I'm drawing a few representative circles. So you can see the circles are created by doing this. We're going to stack our plates as if they were in a drying rack. We're going to stack them this way. Let's check out the radius of each circle. So I'm going to draw just a representation of a radius. I can draw it anywhere. And I'm going to call my radius, since it goes from the center, since it goes from the x-axis to the function, it's a vertical measurement, and I'm going to call it the y value because it starts on the axis. It's the y value. And keep in mind, on the blue function, y is equal to x. So my area is going to be pi times I'm not going to do my area in red. I'm going to keep my red reserved for my inner function. I'll do my area in purple. Hopefully you can tell the difference. Area is pi times r squared. Okay, let's create an integral for that. We're going to go this represents the area of each circle. Dx represents the thickness of each circle. My circles start here and they stack, 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 and they stop at this x value, which is 1. That's going to get the blue all the way around, completely solid. Now, let's work on the red. Let's look at the red. Let's take the red around, see what shape it creates, and then we're going to scoop that out. So, the red, I'm going to draw a couple of circles for you. My red radius is going to look like this. Again, it's dy. It goes from here to the function. I would call it dy. And up there when it gave me equations of my two equations, I went ahead and I thought, you know what, before I get started, I'm going to go ahead and put them both one of them in terms of x and one of them in terms of y. So I changed the red around, but I need the original. So my area is going to be pi times my radius squared. All right, let's set up an integral to send the red around. So again, the red is going to start at the origin, the plates stack. They're just different size plates is all. We're using a different radius. That's all we're doing. So we're going to go from 0 to 1. Each plate is going to be pi x to the 4th. And the thickness of each plate is going to be dx. And now that you've got this, you can certainly do these as separate integrals, or you may combine them. and say, you know what, they both have a pi. They're both from 0 to 1. And they go x squared minus x to the 4th dx. Now, time out for a second. Yes, I'm going to allow you to write one integral. No, I'm not going to allow you to write one area equation. If you don't write two area equations on your paper, you're going to lose credit. And more than likely, chances are, if you don't write two area equations on your paper, if you try to do this with just one area equation, chances are you're going to get it wrong. And because I'm so specific about it, I'm not going to give you partial credit. If you get lazy and you refuse to write two separate area equations, if you refuse to send the blue around, pretend it's filled, send the red around, pretend it's filled, if you get lazy, I'm not going to give you credit. Okay? I'm going to be very, very, very specific. Picky. I'm going to be very picky. But I'm warning you up front, show me both area equations. Once you do your area equations, if you want to set up one integral, I'm okay with that. But you must create two separate area equations. Okay, they get a little bit harder. Let's send this one around the y-axis. So this time, I think you can see, if we look at the kind of the mirror image over here, this time I'm now the red function is on the outside. So spin this banana around the y-axis. Now the rounded part is my outer function. Does look more like a bowl. But on the inside, my bowl has a very linear shape. So, two separate problems. We're going to send the red function around, and we're going to pretend that it's all completely filled and solid. We're going to pretend that for about 1 minute. Then, we're going to look at the blue function. We're going to send the blue function around, and we're going to take that cone that it's going to create. It's going to create a cone shape. We're going to take that volume and just lift it out of there so that we have now created a bowl. All right, so outer first. Let's look at my radius. I'm going to draw a few circles to the outer function. Notice that my circles are stacked vertically. So I'm going to stack my plates from a low Y to a high Y. Okay, we're going around this way, we're stacking this way. Low Y to a high Y. My radius is a horizontal measurement, so I'm going to call it the x value because it goes from the axis to the function. It's the x. Okay, so my area is pi times whatever x equals on my red function. Whatever x equals on my red function. I might want to write these at the top of this page. So I've got y equals x is the blue, y equals x squared is the red, or x equals radical y, depending on which form I need it in. So for this one, I need the x value, so I want my x equals. Okay, I went ahead and squared it. This represents the area of each circle. This represents the thickness of each circle. We're going to start our stack at y equals 0, and we're going to stop our stack at y equals 1. That's the outer. Now let's work on the inner. I can draw a couple of blue circles. You can see that the radius to get to the blue goes from the x-axis to the function. So my area representation for the blue, the area of a single plate, is going to be pi times Vx, which I'm going to need it in terms of y, so that's going to be a y. Start, stop. This gets me everything completely filled in. This is the part that I'm going to scoop out. Yes, you may write it as one integral if you would like. They both have a pi. They both go from 0 to 1, y minus y squared dy. I will let you skip. Let me reiterate here. I will let you skip this step. I will not let you skip this step. You must write two separate area equations. If you want to go straight from there to your integral, you can. You must write two separate area equations. Is anybody counting? I think that's 4 times I've said that. Next one. Let's send the same banana around the horizontal line y equals 2. So that's y equals 1. So y equals 2 is going to be up here. I'm not going to draw it very well, but so this time the banana is going to swing out in a big circle. It's going to swing out really big, and it's going to go around the line y equals 2. Swing out in a big circle. So think about it to figure out how you're going to set up your plates. Your revolution is going to go this way. Can you see the shape of the circle that I'm making? This way. So my plates are going to stack this way. Just kidding. Yes. This way creates the circle. They're going to stack this way. But, yeah, it's like that way. So here we go. The red's going to end up on the outside. So the red's going to be my outer. Now, here's the cool thing. It's going to take some brain activity to figure out what our radius is. What's cool is, once I figure out how to write my radius for the outer function, it's going to be the exact same concept for my inner function. So I know some of you don't like to use your brain. You just like to do patterns. Show me what to do, show me what to do. Tell me the steps, tell me the steps. You're going to have to think this through to figure out what this R is. Once you get this one, then it's the same process. But you've got to come up with how to get this. So if I draw a couple of them, this is going to be hard. Red's going to be way up here. Yeah, that's a bad drawing, but hopefully you can see that I've drawn a circle from red outer down here to red outer up here. My radius. Now I could draw the radius up here, but I'm going to draw it down here where there's more stuff going on. So my red radius is going to look like this. In fact, I think I'm going to draw it here. Yeah, I'm going to draw it there. The circle looked like that. Red radius looks like that. Okay. There's a radius. Goes from the center of my revolution to my function. What do you want to call it? It's a horizontal measurement. It's a vertical measurement. What do you want to call it? Let's call it a y value. Let's not call it the y value, though, because the y value is a vertical measurement that starts on the axis and goes to the function. The y value. If you want to use your function for a y value, this is the y value. That is not my radius. My radius is all of this. So, think about it. From here to here, this is the line y equals 2. So from here to here is 2. I want this part. I don't want this part. This is 2. I want this part. I don't want this part. So I need to go, my radius needs to be 2 minus the y. Two minus the red y. 2 minus the red y. So my area is pi r squared. That represents the area of one red circle. Okay, I told you can skip the part where you do two separate integrals, so I'll skip that part this time. Let's work on the blue. So this is the area of one red circle. Let's work on the area of one blue circle. Cool thing is, the radius for the blue is going to be a y value also, right? And it's going to be the same concept as the red radius. So the blue goes from the center of my revolution all the way to the function. This is the y. I don't want this part. I want this part. So I've got to take the whole distance, which is 2, and I've got to get rid of the y. See? It's the same concept as what I did over there. And for the blue function, my y is just equal to x. Area equals pi r squared. Okay, so I pulled the pi out from each. I wrote this quantity here. I wrote this quantity here. Remember, I'm subtracting the two areas. These are area representations. Subtracting the two areas. And our plates start stacking here, and they stop stacking here. So it's going to go from 0 to 1. Turns out my answer comes out pretty clean. It is 8 pi over 15. I never did this one up here, my bad. This one I got pi over 6. Okay, last one. X equals -1. So I've drawn the line x equals -1, and I will I'm sending this banana, again, it's going to make a big, wide, swooping circle like this. It's going to go all the way around, so it's going to be a bowl shape like this. And I'm going to kind of mimic what it's going to look like over here. This helps me draw my circles. Okay, so this, see how far off the axis of revolution is? It's that far away. So as I revolve it, the banana drawing is not even going to start until here. Hopefully you can see that. You can kind of imagine it. Okay, so it starts its revolution, it starts one away, it's one away over here. The red is going to be on the outside. Red is my outer. I'm going to draw a few circles. Ready? Red to red. This is the center, red to red. So my red radius looks like this. Wow. Radius goes from the center of the revolution to the function. What do you want to call it? It is a horizontal measurement. I would like to call it an x value. An x. I'm not going to call it the x though, because it doesn't. One of its endpoints is not on an axis. It's not on the y-axis. What is the x? Well, the x would go from here to here. This would be anywhere, 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 anywhere. This would be what I would call the x. That's not my radius. My radius is longer than that. This is the x. That's not my radius. My radius goes all the way to here. This is the x. That's not my radius. My radius goes all the way to here. So my radius is always going to be 1 greater. Why 1? Because this is x equals -1. This has a distance of 1 right here. My radius is going to be 1 unit greater than the x. 1 greater than the x. Okay, so my radius is 1 plus, what's my x function? My red x function. My red x function looks like this. Radical y. So my area is pi r squared. Good news. When I go to do the inner, the blue, my radius for the blue is going to be an x value. What kind of x value? It's going to be 1 plus the x value. I just used the blue instead of the red. Okay, and just to show you, blue is going to go from here to here. Just kidding. Just kidding. I did not just do that. The radius goes from the center of the revolution all the way to the function. Okay, there's my blue radius. It's not the x value, it's 1 greater than the x value. Pi r squared. They both have a pi. Our plates are going to start stacking here. They're going to stop up there. So I've got a low y is where they start, a high y is where they stop, and I've got this area representation minus this area representation. Thickness of the plate. And again, hold this out. Don't put it in your integral. Just do your integral. You get 1/2. So therefore your answer, throw the pi back on. Don't forget to throw the pi back on. The answer is pi over 2.